Welcome to another video. Video about thermodynamic property relations, and especially about partial derivatives. And in this video, we will discuss how a bag of crisps, the volume of a bag of crisps, behaves. And during this video, we're going to take this bag of crisps for a walk up to the Himalaya from point A to point B at the top, point B, and here we have a temperature TB and a pressure PB. Over here we have a temperature TA and a pressure PA, and of course we have here our bag of crisps. So crisps, and well, at high in the mountains pressure is very low, so PB is lower than PA, and high up in the mountains temperature is usually lower than temperature at sea level, TA. And we're going to bring this bag of crisps with us to the top of the mountain. So the bag of crisps actually undergoes a process. And to show you an example of a process and what happens during this process from point A to B while lowering the pressure, we have a short movie. So please enjoy. Over here we have a vacuum chamber which I connect to a vacuum pump, and I'm going to show you that by lowering the pressure in this vacuum chamber we can actually increase the volume of the bag of crisps increase. So there we go. We know for sure that the volume of a bag of crisps, and we're just going to consider the amount of air that is inside the bag of crisps. We know that it's dependent of the pressure and temperature. And it is dependent of pressure and temperature by the ideal gas law, RT over P. And we're actually very interested in how the volume of the bag of crisps changes. So we're interested in change. So we're interested in dV, the change of the volume. And well, if I want to know something about dV, we've already learned that we need to take the partial derivative since temperature and pressure are involved. So this will lead us to the following differential equation. dV is equal to the partial derivative of volume with respect to temperature for a fixed pressure multiplied by dt plus the partial derivative dV over the pressure multiplied by dP. So here we have our total derivative of the volume. And using this, and of course we are going to assume that dt and dP are very small, so everything is in quasi-equilibrium. So we're going to, well, cut the process in very small slices, but in the end we can get a good view of the behavior of the bag of crisps, of the volume. Well, since we know our function of the volume, RT over P, we can actually calculate dV over dt for a fixed P, which is the derivative of the volume with respect to temperature. And this will be R over p. And it's actually the same as v over t. Use this equation and you will find out. Please check it yourself. And we can determine the other derivative, partial derivative dv over dp with respect to a fixed temperature. And this is, well, actually minus RT over p squared, or equal to minus v over p. So here we have our partial derivative of volume with respect to pressure. Okay, so our total integral will look like this. dv is, let's just say now r over p dt minus r over t p squared dp. So this is the total derivative of the volume. Now, of course, I'm interested in the behavior of this bag of crisps, of the volume of the bag of crisps. So I'm going to draw the diagram, the surface related to the volume. And the system of coordinates looks like this. Over here we have our temperature, T. Over here we have the pressure, P. And over here we have the volume, V. And to make this diagram, I have to check how my volume behaves for instance, a fixed T or a fixed pressure. So I'm going to fix my pressure. Then volume will behave like a constant multiplied by the temperature. So R and P are both constants, so it will be a constant multiplied by the temperature. And in my graph, it will look like this. So a constant multiplied by the temperature, so a straight line. So now I'm going to fix the temperature. So for a fixed temperature along the pressure line, I'm going to study the volume. So that will behave like RT is a constant over P, dus a constant divided by pressure. So that will look like something like this. So 1 over a variable. Well, and I know if that happens here, behavior will be the same on this side. So I can just try to draw a parallel line. And over here, behavior will be comparable. Okay, so let's assume, so this is the surface of the volume. So this is how the volume is described by pressure, by temperature. You may remember this surface from the exercises, the PVT diagram. Now I'm interested in the behavior at some point along the, at some point in my diagram, at some temperature and some pressure. So I'm just going to, well, at first I'm very interested in what happens for a specific pressure. So, and let's say that's this pressure. So there will be a line here for this pressure. So for this pressure I have my CT diagram, and at some point I'm interested in the behavior. Well, and since I already know that my dV dt for a fixed P is equal to R over P, so equal to a constant since P is fixed, I know that my derivative over here, so my rate of change over here, is a fixed value, so a constant value. So over here I can show you I have my dV over dt, so my rate of change due to temperature for a fixed pressure, which is equal to R over P over there. I can do the same in the other direction. So on this line, and for instance check the behavior over here. Then I can make my derivative will look like this. So it will describe the rate of change, and my derivative in this point will be dV over dP for a fixed temperature, and it will be equal to minus V over P. Well, in this I think it makes some sense, since if we lower the pressure, the volume will increase, like you can see over here. So for a fixed temperature. So, and that's actually what we saw in this experiment. When we decreased pressure, volume increased until it could no longer increase, and the back of crisp would open. So I hope this example gives you a bit of a feeling why we need these partial derivatives and what's the use of them. And I hope this will help you to apply the partial derivatives in completing your assignments and your project. Good luck.